All right, let's do a few fluid flow examples. So let's start by looking at some flow through a pipe. So let's say we have water in a pipe, and it is in a 10 centimeter pipe that is moving at 2.1 meters per second. 2.1 meters per second. And let's say this pipe then gets bigger. There's some kind of expansion, and the diameter of the pipe increases to 20 centimeters. What is the velocity over there? So without doing anything, we should at least be able to guess if the velocity is going to speed up or slow down. So think about that. And then let's look at this. Okay, so we know that V in, A in, I should say, first of all, water is a liquid, and the density of water is not going to change between these two ends. So we can use our liquid equation. We don't have to use our general fluid equation is rho AV. So we can, for water, rho is staying constant, so we can just use A times V. So we have A in V in is equal to A out V out. And we know A in, we know this area, we know this velocity in to our system, and we also know this A out, this 20 centimeters. It turns out it doesn't actually matter if this pipe is circular or square for these calculations, but let's assume it's circular just to make this a little more challenging. So the area of this inlet is pi r squared, so that's pi times r, which is half of 10 centimeters, 0.05 centimeters squared, times our velocity in, 2.1 meters per second. And that's equal to our area out, which is pi r squared for half of this, which is 10 centimeters, times our velocity out. So solving for V out, we get pi r squared over pi r squared times 2.1. So that's pi times r in squared over pi times r out squared times 2.1. So here you can see the pi's are going to cancel, which is what is telling us that it didn't matter that this was circular to begin with. It only tells us, we only have to worry about the ratio of the diameters or radii, and really the ratio of the squares of those. So if our radius doubles, it goes from 5 to 10, or the diameter goes from 10 to 20, the area quadruples, right? It increases by a factor of 4, which means that our velocity is going to decrease by a factor of 4, and that is what this is, right? 0.05 squared over 0.1 squared is 1/4. So we're going to get 2.1 times 1/4, and that's equal to 0.53, if we round to 2 sig figs, meters per second. So our velocity decreases by a factor of 4 over here because our area has increased by a factor of 4. So that's how this continuity equation stuff works. If the density changed from one end to the other, of course, we would have another term multiplying each of these, but that would be something that we would know and could use in this equation. All right, great. Let's do an example now using Bernoulli's equation, and let's do one kind of non-example because I think there's kind of something cool that we can get from Bernoulli's equation. So that is, let's say we have a container of liquid, and we want to know what the pressure is at some point down here, and we don't have any significant velocity. So we want to know what the pressure is here, and we know that this is in air or something like that. This is P atmosphere up at the top. Okay, so we can find the pressure at this point using Bernoulli's equation. So we got to label our points A and B. So I'm going to label this point A and this point B. So we want our pressure at point B. That's what we're trying to find out. Now this is just sitting here not moving. So our velocity here is equal to 0. Our velocity here is equal to 0. So there's no kinetic energy that matters in this problem. And there is a height difference between the two of some distance y. That's what we're trying to, we're trying to find the pressure at depth y. So Bernoulli's equation says that kinetic energy plus potential energy plus pressure at A has to equal kinetic plus potential plus pressure at B. So at point A, V equals 0. So we have 1/2 rho 0 squared plus the potential energy at A, so that's rho gy A, which is what we're calling y here, and the pressure at A, which is this atmospheric pressure. So this has to equal all of those same things calculated at B, where there is also no velocity, where now this height is what we are calling height equals 0, right? If this height is height y, this height is height 0, plus this pressure at point B. So if these two things are equal, this is 0, this is 0, this is 0. That means that the pressure at B is equal to the atmospheric pressure plus rho gy. And wouldn't you know it, this is exactly our depth pressure equation that we learned about before and that we can derive from like free body diagrams. So this is just for fun. This is just showing that this equation comes out of Bernoulli's equation. This equation is because of conservation of energy, as well as from our force way of thinking about it from before. Okay. Not a real example, just kind of a fun look. Okay, here's a real example. So let's say we have that same container of water, but now we punch a hole somewhere towards the bottom. So there's a hole in this container. And this, I said this is water, obviously it doesn't have to be water, that's just kind of the go-to liquid for these examples. So let's say that we measure the velocity of the fluid coming out of the hole, and we measure the velocity is equal to 11 meters per second. So the question is, what is the height of the fluid above the hole? We don't know enough to find out the height above the bottom, but we can figure out what the height of the fluid is above the hole. What is this height equal to? Okay, so fluid flow, Bernoulli's equation problem, especially, there's a change in height here, so that's another clue that we should use Bernoulli's equation. So let's, if we're going to do that, we have to label our 2 points. So 1 point, our strategy for picking these points A and B for Bernoulli's equation, should be where we know the most. So we know a lot at the surface. We'll call that point A. And the other point where we know a lot is where we know this velocity, right? So where we have this 11 meters per second of velocity, we're going to call that point B. So what do we know? Well, let's start with point A. Yeah. What do we know in terms of our different kinds of energy at point A? Well, we are at a height h above where we're starting, so we have potential energy at point A. The pressure is not specified here, but since we're not told otherwise, we're going to assume that we have atmospheric pressure in the air around it. So that is going to be the pressure at the surface for point A, our atmospheric pressure. Lastly, do we have kinetic energy at point A? Is our fluid flowing very much? Well, as long as this hole is smaller than the size of our container, as we're letting fluid out the bottom, yes, the fluid at A is going to be moving down, but it's going to be doing so very, very slowly. Even if you're talking, a centimeter per second, which is a pretty fast rate for this fluid level to drop, that is pretty small in terms of velocities, and so it is effectively negligible. We can look at those specific numbers if you guys are interested. Ask during office hours or during our lecture times. So my assertion then is that at A, our velocity is equal to 0, or at least very close to 0. Our pressure is equal to atmospheric pressure, and our height is equal to this value h. At point B, we know our velocity, it's 11 meters per second. Our pressure, we're going to deal with in just a second here, and our height is 0. So if we call this height 0, the height at A is this h value we're trying to find. Okay, pressure at B. So whether we take B as being just outside or just inside the hole makes a difference here. And the reason is, if we try to think about what's going on inside the hole, this point is still feeling pressure from the other fluid pushing on it, pushing it out the hole, that's going to cause it to speed up. So if this velocity is the speed that the fluid is coming out the hole, we need to pick a point B that is just outside the hole, that's not being pushed on by this fluid inside anymore. What is it being pushed on by? Well, it is only in contact with the air, so it's being pushed on by the air. So in fact, the pressure out here is also just the pressure of the atmosphere. Once you get outside the hole, you're not being pushed on by the fluid in the bucket or container anymore. You're just in the air, and so that is the pressure that you feel. The result of that is that when we go to plug these into Bernoulli's equation, these pressures are the same, and so they are not going to matter anymore. Okay, so let's write this down here. So for point A, we have 1/2 rho v squared, v is 0, plus rho g y, that is our height h, that's what we're trying to find, plus our pressure, the atmospheric pressure. So that is equal to that same stuff at B, that is 1/2 rho times 11 meters per second squared, plus rho g y equals 0, plus the atmospheric pressure at point B. So like I said, these two things are the same. I said before, we could also think about that in terms of gauge pressure. So if we think about the gauge pressure at point A and point B, the gauge pressure there, the difference between those points and atmospheric pressure, is 0. So the gauge pressure at both those points is 0, so you could just easily say those are both equal to 0. Anyway, it doesn't matter, they're going to cancel. So this is also 0, this is also 0. So we're left with rho gh is equal to 1/2 rho v squared. And this v is the 11 meters per second at point B. So notice that the density here cancels out. So it doesn't actually matter in this particular problem whether we're looking at water or some other liquid. The densities at these different points is not going to matter. So we could plug in 1,000, but we're going to have 1,000 on each side, and that's going to cancel out. Okay, so if we want to solve for h is equal to, so divide both sides by g, so we have 11 squared over 2 times 9.8. So that's 121 divided by roughly 20. So that's going to give us a height of roughly 6 meters. If I plug that into my calculator, I get 6.2 meters. So in order for this to be true, 11 meters per second is pretty fast. You need 6 meters of fluid above the hole. That's like 18 or 20 feet of fluid. All right, so in real life, this answer is going to be a little unrealistic, and that's because Bernoulli's equation assumes that there's no energy lost anywhere in our system to non-conservative forces. This, of course, is not 100% true. We are going to lose some energy, and the biggest place that energy goes in flowing fluids is to what's called viscosity. So just like how if you have a block rubbing over a solid surface, it loses energy to this friction force, fluids flowing rub against themselves and lose energy internally to viscosity. So the measure of a viscosity of the fluid is how thick it is, how much internal friction it has, how much energy it tends to lose because of that flow. So if you have a setup like this, if you have a big container full of water and you measure the velocity of water coming out that hole, that velocity is going to be different than if you have that same container filled with something like honey or syrup, something with a much higher viscosity. Because of the higher viscosity, that's like there being more friction, and you are going to lose some of that energy and not end up with as high of a velocity. So that's what we are talking about when we say if a liquid is like really thick, it has a high viscosity, it does not like to flow without losing energy. There are fluids that don't lose energy. Those are called superfluids, and liquid helium can be a superfluid, so you can have energy perfectly conserved from point A to point B. That's pretty fun. It only happens at super low temperatures. If a fluid does lose energy to this viscosity, just like friction, that energy is going into heating up of the fluid itself. So if you have your honey flowing from point A to point B and it's not going as fast as you expect at point B, you will see that the temperature will have increased from where it was, and so this energy is going into heating up of the fluid, and that's what this thermal energy is what we're going to learn about in our next chapter.